Already listened to Alexander's presentation at the previous next hop. Let's talk about segment routing and its data plane, but we will also touch upon other issues. Let's listen to how you worked together. Thank you, Andrei. Good afternoon, dear colleagues. It's very nice to have such a big audience here. It's after lunch now, but we still have a big audience. Thank you very much. My name is, once again, Boris Hasanov, network architect, as I already said. So we are finishing the introduction stage, and now we are moving on to the next one. You probably heard about this technology, segment routing, because any vendors conference can't do without this point. Some people have already tested this technology, so I hope you are aware of this technology. In the second part of our presentation, Alexander will tell us about how segment routing is used. So people started talking everywhere about this technology a lot of years ago, back in 2013, and you've probably heard about it. But before talking about this technology, we need to understand why should we have it. Right now, we have the normal IP forwarding and the classical LDP, and we have two different protocols, such as RCVP and RFC. And we've been using these two protocols for traffic engineering for a long time. They have a lot of positive features and advantages. I'm not going to list all of them right now. You are well aware of all of them. But they have certain limitations as any other technology. Talking about the LDP protocol, we always have to build a tunnel via the protocol for dynamic routing. So traffic engineering is quite problematic in the event of LDP because you will need to face metrics, and there is a lot of noise as well, and you have to synchronize different things there. As for LSP and TE, which enable traffic engineering there and choose the shortest path, those methods already have some limitations. That is, the need to support forwarding state at interim devices. And the next point is that there is a dependence on the number of LSP. And this depends on the number of PEs that we have, which is not convenient either, particularly if we have a lot of PEs. To conclude, it's quite difficult to configure these networks manually. So instead of trying to respond or to find a technological solution to these issues, the technologies of segment routing was born. It uses source routing, as you can see on this drawing. And you can see that our incoming PE or ingress PE determines the number of packets along the path, and it adds labels to those packets. And in the simplest option, one segment is enough in order to get from the source node to the destination node. And this segment is a kind of tool. It's about the topological feature. And as we talk about segment routing, something that we can simplify by doing LDP and RSPTE, So we first use those segments for LGPs. That is the additional expansion to other mechanisms. And to be very brief, I don't have much time, but I would like to remind you about the types of segments that we have if we use segment routing. First of all, it's probably the basic segment, prefix or node segment, which is unique. It's either prefix or a particular router are determined. And as I already said, there is the IGP expansion that we use. There is also a technology or a method that identifies the router's interface. We can identify a segment which is connected with a specific router's interface. There is also another method which is pretty convenient, and this is called Anycast. And there is also the binding SID. This is probably the most multifunctional SID, which has a lot of features. And I'm going to talk about one of its applications. And there is a type of SIDs which are connected to BGPs and which are used in architecture where we need traffic engineering between different autonomous systems and design on this basis. What segment routing can we have, colleagues? There are different types of segment routings. I can't tell you about all of them, so let's focus on two most important ones. The first one is MPLS, or SRMPLS, at the forwarding level. And this routing segment is similar to our favorite MPLS. This is where SID is passed on as an index or an absolute value that depends on the vendor's implementation. It has the format of an MPLS label. It also supports all the features in the classical MPLS, which is set on this slide. And furthermore, we can have a best effort, SRBE, that is the shortest path, and there is also SR traffic engineering. And there is another important branch of segment routing development, which is called SRV6. And it is different from MPLS because we do not use any MPLS at the forwarding plane. And the prefix SID is an IPv6 address. In case of traffic engineering, there is another heading or routing header, which is called SRH for SRV6TE. And this is where we write down a stack of our SIDs. And the first SID is going to determine our next hop. And this is how we run through all the routers that we have in the network. And there's a key moment which differentiates SRV6 from the other system, is that its SID consists of two parts of varying lengths, the locator and the function. And I also included some backup slides at the end of my presentation which showcase those functions. This is how the segment routing is working on the level of forwarding. If we need to transport the traffic from PE1 to PE5, and if SID 16005 is generated, then it goes back to PE1. Then there's VPN 16005, and it goes to PE5. If there are two paths with the same metrics, then there will be a hashing towards those paths. The traffic will be transferred via the same path. If we have traffic engineering, we should add a configuration. We should describe the explicit path for our router, or somebody has to tell us about it, some external system. There is a difference with SRV6. Those identifies SID. You have some brief information about them below the slide. Those identifiers are able to give a unique identification of a router with this SID. They will tell us that this router will interfere with our package somehow. And we are going to flood this SID. And at the forwarding level, you can see the 6 PE, and there is the VPN SID that we have at the exit level. If we have a VPN network, the packet goes via our nodes, and then you can see the next SID, which is copied to the destination address, and the count of the number of segments goes down. Here is a short description of all those technologies. And you can see here on this table that there is a difference between those technologies. You can see whether it's easy to program all those technologies or not. I'm not going to describe this in detail. And of course, we all bear in mind that we might have a good possibility to pass on the traffic via the shortest path, but we still need traffic engineering. In the classical solution, we have a system that signals how to dispatch this data and how to distribute the labels. But how do we organize traffic engineering? The first attempt of implementing traffic engineering is a mechanism which is called Flux Algorithm, flexible algorithm, or Flux Algo. The idea is to calculate different options of possible paths based on an algorithm definition. Some additional metrics are used for that. Thanks to the IGP protocol, we can build different paths, and they can have different values ranging from 0 to 255. There are different SIDs between the paths, and as a result, depending on the service, there will be one or other topology. So this is the next step towards traffic engineering. It looks pretty interesting, and Alexander will tell us about it later in greater detail. But if we need full-fledged traffic engineering in its classical meaning, we need to have an exterior mechanism that would read those complicated topologies. We need to calculate the topology, and for that we need the PCE computation element, which computes the optimal paths, and it works with traffic engineering database. And it's important. We'll see why. I'm not going to tell you about PCE's advantages. It's the offload of routers from heavy computations. The routers become clients based on path computation clients, PCC. There are coordinated computations and so on. But the key question is how to get this traffic database device or controller, which describes our links within the network and the limitations that we want to use. So we can get them from the link state database or from the outside. If we get it from LSDB, we need our controller and PC functions to have interfaces with all IGP domains where there is a major issue. But this solution is not really scalable. The other option is to expand the BGP protocol, which is called BGP link state. I'll tell you more about it later. And we can have the traffic engineering database via the PCEP protocol. The industry currently uses both approaches, but the most common one is called BGPLS. Here you can see more information regarding BGPLS. There's already RFC, and your link state and LRI, which describes the link, and we also have some other systems. And there is also the PCEP protocol. That's the second type of PCI, which works with the routers. And the protocol works on top of TCP. The routers become the clients of PCEP computation clients. The servers interact with each other. And the most important thing is computation request and the report, in which the controller gives the computed path to the router. And that's not all of it. It's good to have a PC, but it's not enough. Ideally, we need a structure with a more complex hierarchy based on traffic engineering. And this more complex hierarchy is the SR policy. This is a structure which links a number of segments, because our traffic engineering is determined by a number of segments. So this structure links those segments to the specific target or intent. And there are three parameters which characterize the SR policy, which are called headend, color, and endpoint. And we have some candidate paths here. And you can see the SR policy at the bottom of the slide. We can see different paths or candidate paths here. There might be many different candidate paths. Each of them has a certain preference level. Some of them are more preferable than others. And it's important to do balancing, both equal and unequal balancing. Compared to the classical TE, you can see the differences here on the screen. Last but not least, this is where I would like to finish my introduction part. That is the technologies that decrease the probability of failure, such as MPLS or another technology. And we have the LFA topology there. I'm not going to tell you what it is about. Most of the listeners are aware of this technology, but we need to move this traffic to the next hop so that it doesn't get back to us, because we don't need this traffic. And this LFA technology uses the topology-independent LFA and the construction of a tunnel, and it also has a list of segments which will be delivered to the router that will not send the traffic back to us. And it works even in the most complex topology, where RFA or LFA does not work. So this is exactly the technology that functions well in combination with segment routing. But it's noteworthy that LFA and the SR policies I mentioned do not work together. They don't know anything about each other. So the best backup path should be used within the SR policy.
And the last slide, because I'm a little bit behind the schedule. This is an option of using the binding seed, which I mentioned from the very beginning. This is when we can use that under the slogan mirror seed. So this is the same binding seed, but this is how you may protect egress PE. When we see that BE3 wants to back up PE, we actually do the mirror seed, and it mirrors that start flooding, and so it means that PE3 will protect PE2. As soon as the routers would get this announcement, this statement, they would make the fast read around on the redundant next hop, one indication of PE2. So once something happens to PE2, we don't any longer have to update the egress PE. We can immediately, at the level of P, switch the traffic to the second PE. So this is the idea behind that. So the binding seed can be used in order to protect egress PE. This is also being used for SR policy protection. With that, I have to conclude my remarks, and because I have run out of time, I would like to pass the floor to Alexander Klimenko, who will speak about the second more important part, the place of SR in Yandex network. I'd like to thank Boris for getting synchronized. We'll now understand what options of SR are available there. My name is Alexander Klimenko. I'm doing a lot of interviews for Yandex, and very often I'm asked about control of the network. iBox in the network will manage to answer the very first question only, probably not even exhausting the question. SR implementation is no longer a testing or pilot project. And the main idea of my project is to show the route which we have made, to showcase certain problems we run into. Probably it will help some of you to solve the same problems. I will show how DSI looked before, what helped us to start the same project with the segment routing. Before, actually, we had more than 100 devices within PE, based on a generic chip, and whatever you do for the operational system, this chip will not work better, and the structure, the hierarchy, leaves much to be desired. And we certainly saw the problem with the folding, with compatibility. All the sources started with the spine of the first year. So one more popular question is whether you have common data center. We used to have it, so everything has changed, and we actually outsourced the edge port routers, and the services start from there. Therefore, we can develop from that, and we can use SR using the old equipment. The second thing is how we divide our topology. We used to to say that we have fastbone and another type of network. The division of these processes is done using two different routing processes, so that the traffic goes to one of the topologies. In the announcement, actually, we put either backbone or fastbone topology, depending on the address. In the traffic engineering, we already have ESRP. Why traffic engineering is needed? It is because actually you get connected to the network kernel, and that's it. Now we have data-centric channels and links, and we have foreign channels as well, and DC connections are no longer sustainable, and we need some control within the backbone. This is a nesting doll. The services of 6P, 6LPE on top. And there is a standalone piece of fastbone network. Why we need SR? Just to get rid of state from the old boxes, to mend the topology, make it more regulated, to disseminate the traffic into different links, and to use the links differently. You don't have to think that once you engage SR, everything would work smoothly. What we saw, actually, we looked at SR MPLS versus SRV6, what to choose. 6 months ago, the vendors did not provide for the compatibility. And in terms of the operational standpoint, the transition from stack to MPLS looked much better. Therefore, we solved that problem quite easily. Actually, we thought about dividing these routing processes. We thought whether to divide that into fast bone and backbone, but we realized that probably this can no longer be used. Let me draw an example. One of the vendors of the network equipment implementation of the second option is separate or standalone logical router, and it would get with the special stamp. Certainly it can be redone and it won't be overcome, but this approach is no longer the best and the most optimal. Therefore, probably the division into two processes is no longer applicable, and we can use either SR without TE, but there would be a problem with fastbone. It lies in the head that however many links you will give, it won't be just marked. From time to time, we'll see the picture like the one on top bottom, on right bottom, when the whole band will be occupied. Next option, we'll speak about the division of the networks. So we're speaking about QoS-based approach. Several tunnels are being built. One of the tunnels actually would have one kind of DSCP, and the other tunnel would be engaged with the different kind of DSCP. The disadvantage is that we'll have to control all the nodes within that network, and probably will not resolve that problem until the end of this year. So, for instance, the machines within the data centers, so they want to download the software, and you have to control the DCP. You decided to update some switch in the lab, and you have to control the ink. Therefore, this QoS was not applicable. The approach when you use some single process for backbone and not to use that for fastbone is not an option because it will overload the network. The options, everyone who is fond of SR may remember, this is SRTE and Flux Algo. SRTE similarly suits us very well because it is very simple, very native, but the tunnel between two PE units could be built only to one seed node. So it means that we have certain address of PE unit which is being used as the router ID, and we give node seed to that. You build the tunnel to that unit. Once we give one more O back and one more node seed, then some vendors did not allow to build one more tunnel, and this was not an option for us. Flux Algo is a super thing, and hopefully, similarly, this was our case. When you define topology, you build certain SRT channels within Flux Algo, but it turned out that the vendors do not support 3 Flux Algo topologies. They only planned for that. So what we came up with, we are using SRX Policy. This is a thing which looks very much TE, classical TE. Between two pairs of TE, we would offer two kinds of SRX Policy, one for fastbone, the other one for the backbone. We're using segments of sheets, and within the policy we have simply up to 8 paths, which we're using. Certainly, it's not very convenient to do that manually, but I will not have time to tell you more about that. Also, this nightmare embraces our other routers. Another problem we are facing is that not all the vendors believe it is necessary to update the routers even within the segment sheet. For instance, if the neighboring station fails, still this policy remains valid. And to conclude my presentation, let me tell you that SR is no longer just want-to-have technology. It's being released for quite a while, and we are not an exception. But you don't have to think that SR can be installed at your network with no efforts. I invite you to start doing that immediately and approach the vendors. You are the clients, the engineers who are defining the vector of the technology. That's it. Thank you so much. Thank you so much, Mr. Klemenko, Mr. Hasanov. We are behind the schedule a little bit, but it is worth doing that. And some questions. I think that it is a very interesting topic. First question goes from Roman. As expected, condition is not forward in low-band internet. Don't you think that SR over EDP is more attractive for the use of internet? If you are speechless, then please unmute your microphones. Apologize. I muted my microphone. In terms of SR over OIP, has been written the RFC. Actually, we didn't have time to speak about that. They have their own advantages and disadvantages. But first, look, colleagues, I understand that when we're speaking about the technology for tunneling technology and overlay structure, we are speaking about more local spectrum of application. We're speaking about our own or corporate network, which is controlled by us from in out, and we're responsible for that. Probably in future, there will be similar global networks, but we employ more local scope, where this is not a problem for us. Okay. There was a question whether Yandex is using SR and SRTE. There was a question about the multicasting and VPN, so let's skip it, because this is not our case. We are not speaking about multicast. And just a brief comment on that. Multicast, this is a separate technology. And SR, this is a standalone technology, and would need either beer or beer with. So the chat members also speak about beer, and there would be discussion with Jeff Tansura, who actually also is very fond of beer and beer SF. So one more question I will skip. Question about what kind of employee seats are there available in Yandex. I think that we have exhausted the questions. I think that people are very much moved by these topics, and we are controlling that. And that cost topic actually is a very big story for us. In the light of the year, we cannot guarantee that nothing would happen. We have TOR, where we would mark something, and there are security LCR there on that TOR, and all of a sudden it goes into the same TCOM memory. So if something goes wrong, the traffic would be unmarked. Sometimes it may happen, so we could not guarantee at that moment that within a year's time everything would be good and 100% controlled. Okay, and the last question for today. Have you ever run into the depths of stamps at the current hardware? No, at the current hardware, we don't have such problems. We have enough stack stamps, and it would be done by a smart device. The H-code routers, which are doing only pop-up stamps, and there is no problem like that. A brief comment or some addition to complement what has been said. Even such problem arises. We have the notorious bind seed, which helps us to address that problem. Thank you. Thank you, Boris. Thank you, Sasha Volk. I think that this topic was very interesting for our viewers, and guys are waiting for us on chat, and we are proceeding with the second presentation.